Hi, good morning my dear students and welcome to the world of electronics. Our activity for today will focus on lesson 2 of module 2 under LX111, which is electronic devices, instruments and circuits. This lesson is all about capacitors. All of these capacitors will be taken today. So capacitors are electronic devices that are capable of storing electrons as an electric charge. Electric charge, by the way, class, is an electrical energy or voltage which are stored on the surface of this dielectric material. And it is said that capacitor is like a battery that can be stored with voltage. Okay, let us find out. Okay, we have here a capacitor with a capacitance of 2200 microfarad with a working voltage of 50 volts. And we have here a battery. And let us measure first what is the voltage of this battery using this analog multimeter. We will use 10 volts as a voltmeter range for measuring the voltage here. DC voltmeter, because the voltage that is at this capacitor is DC. So we have here the positive side and this one is the negative side. So it reads here 9.5 volts DC, 9.5 volts. So let us try to connect the negative side of this battery to the negative side of this capacitor. And the positive side of this battery is connected to the positive side of this capacitor. Okay. Let us wait for several seconds. Now the current is flowing through the capacitor, and the capacitor now is storing this electrical energy or electric charge, no? So probably the voltage now is full. No, the voltage that will be filled up or stored in this capacitor should be in accordance with the voltage applied. No? Whatever the amount of the voltage will be the amount of the voltage also that will be stored in this capacitor. Okay, let us prove. Okay, let us now measure if there is an stored voltage of this capacitor. We have here the negative side and the positive side. So it is 9.5 volts using 10 volts range. Or if we will use 50 volts, the same. Okay, it is. We are using the range here 50, so we are going to read 50, 40, 30, 20, 10. That is below 10, no? So the amount of the voltage now is stored in this capacitor actually is around 9.5 volts. The same with the amount of voltage here in this battery, no? But remember, capacitor will not retain the voltage for a long period of time. So let us measure. So little by little, the voltage actually is descending or reducing, no? We will use 10 volts in such a way that it is clear to our eyes. Okay? So little by little, the voltage will be reduced or will be discharged from this capacitor. Because how long does the voltage retain in this capacitor? That depends upon the capacitance of the capacitor. The ability of the capacitor to retain or to accept electric charge depends upon the capacitance and the voltage applied to it. The higher the capacitance, the longer the time to retain the voltage in this capacitor. No? Or the lower the capacitance, the faster to discharge it. It won't stay longer. Okay. Okay, what is really this capacitor? In what way that the electric charge is formed or built between these two conducting plates? Because here we will try to figure out. We have here, because it is said that capacitor is constructed out of two conducting plates. Two conducting plates. It is made of conductor. And we have here the terminal here. They are not physically connected because the two plates are actually separated by insulator or the so-called dielectric. So, before we go further, let us first explain what is this conductor and insulator. Actually, there are three kinds of materials. So what are these materials? We have the conductors. Conductors possess low resistance. If it is low resistance, it allows freely the current to flow. Okay, what are these conductors? Okay, we will use times 1 ohm as the lowest range of an ohmmeter. That will measure the continuity or the resistance of this conductor, no? Okay, we have here an aluminum. The resistance is very low, 0 ohm. How about this steel? Low resistance because it is a conductor. Okay, what else? Okay, steel. It is covered with insulator. Okay. Another example of steel. What else? Silver, bronze, manganese, constantan, tungsten, nichrome. Those are examples of conductor. They possess very low resistance. They allow the current to flow. That is why when you are holding a metal made of iron, for example, or made of steel, or made of aluminum, when you suspend it to the terminal of the outlet that distributes 220 volts, you will be electrified. Current is passing through that conductor. No? That proves that the conductor really allows the current to flow through. No? Okay. And what are these insulators? Insulators are those materials which possess very high resistance and they don't allow the current to flow. So an example of, okay, let us prove using the highest range to measure the resistance of these insulators. Set, short the two test rods. Usually the pointer deflects to the right portion. We will set it to 0 using the 0 ohm adjuster to have an accurate reading again. No? Plastic. It doesn't move the deflection pointer. That proves that it is very high resistance. Infinity. It is not measurable. Air is a good example of insulator. It won't move the pointer. So it is very high resistance. How about this plastic again? The paint. The paper. So, the cotton, they possess very high resistance. Then another insulator materials are acetate, cellulose, polyester, mica, mylar, electrolyte, ceramic. Those are examples also of insulators which possess very high resistance. Current is not allowed to flow. That's why if you hold this terminal, this plastic, then try to touch it to the live wire here. The current is not allowed to flow. You are not electrified because this possesses very high resistance. Then the third material actually is the semiconductor material that belongs or between the extreme of insulator and conductor. Good examples of semiconductor materials are silicon and germanium. Okay? We have here an example of no. Okay. Usually, okay, we have here a diode which is constructed out from silicon material. Remember that there are two kinds of semiconductor materials. These are the silicon and the germanium. Okay, again, using the ohmmeter here, let us measure the resistance of this diode, which is made of silicon. So it is a conductor because the pointer deflects lower, no? But when it is reversed, the resistance is very high. So open, current cannot flow through. But here, current is allowed to flow. So this is a good example of semiconductor material. So unlike the conductor, that both sides, current is allowed to flow. For the insulator, current is not allowed to flow. Okay, those are the three kinds of materials. So again, let us go back to the construction of this capacitor. It is said that capacitor is constructed out of two conducting plates separated by insulator. Okay? So, how the capacitance of this capacitor is determined? So, the capacitance is greater when the plate area of the conducting plate is larger. And the conducting plates are also closer to each other. The capacitance there is higher. But when the area of the conducting plate is smaller, especially if the area or the distance between them is farther, the capacitance there is lower. Okay. It is said that the ability of the capacitor to accept electric charge depends upon the capacitance. The higher the capacitance, that is the larger the plate or the closer the plates, the more the number of electric charge is being stored. Okay? Especially if the voltage is high also. With a basic formula, Q is equal to CE or CV, where Q is an electric charge. The unit is coulomb. Then we have here the C, the capacitance, and the E is the electromotive force or the voltage. No? For example, if the capacitance here is 2,200 microfarad, and the voltage applied is 10 volts, so that is how much? Times 10, 0, 0, 0, 0, 0, 0, 2, 2, 0, 0, 0. So, it is 22,000 microcoulomb. The unit for electric charge, by the way, for Q is coulomb. No? Microcoulomb. So, the higher the capacitance, the higher the charge. Or we call it electrostatic lines of force, attracting from electrons to protons. Protons attracts the electrons from the negative side of the battery. Whereas protons originated from the positive side of the battery are actually accumulated at this plate, whereas electrons coming from the negative side of the battery are also accumulated at this plate. Then there is a force of attraction. We call it spark. Or, strictly speaking, we call it electrostatic lines of force. So the electrostatic, there are more number of electrostatic lines of force, which is now the 22,000 microcoulombs existing between the two conducting plates. It is now stored at this insulator or dielectric material. No? That is how the electric charge or the voltage is stored between the two conducting plates. It is stored at the dielectric material. And what is this dielectric material, by the way? Dielectric material is actually the insulator. That's why we have here, capacitors are named after the dielectric used or the insulator being used. For example, electrolytic capacitor. The dielectric material or the insulator being used is electrolyte. We have here polystyrene is among the insulator material or dielectric material. There are two conducting plates separated by this polystyrene insulator or dielectric material. Polycarbonate film, mylar. Mylar is also a good insulator. Then we have ceramic. Then polyester, polypropylene, ceramic disc, polypropylene again. Air is a good insulator. Epoxy is among an insulator. Silver mica, no? And we have here plastic film capacitor. So, they are named in accordance with the dielectric used, or the insulator being used, that separates the two conducting plates. Okay. Now let us now come to the numerical code, the capacitor numerical code. Like resistors, resistances of the resistors are identified by their colors. Now, there are three resistors here wherein the resistances can be read using their colors. But most of the resistors, the resistances are read using the numerical code, resistor numerical code, which are printed on the surface of the body. No? Just like we have here, this is 4.7 ohms J. So that is 4.7 ohms with a power rating of 10 watts is given here. No? It is inverted. Okay, J actually is the tolerance. JKM. J is more or less 5%. K is more or less 10%. And M is 20%. More or less 20%. Those are the numerical letter or numerical code. The letters there are the tolerances. So they're actually given. No? Just like, but in a surface mount device or the chip resistor is also called a surface mount device because the resistors are mounted on the solder side of the PCB. No? We have heard the component side and we have heard the solder side. Using the chip resistor or the surface mount device is MD. No? They are actually mounted on the surface of this solder side of the PCB. So we have also for the capacitors, there are SMD capacitors or chip capacitors also here, which are mounted on the surface of the solder side of the PCB. Okay. We have here for the electrolytic capacitors. Actually, some of the capacitors are polarized, like electrolytic capacitor aluminum, electrolytic capacitor oil impregnated, electrolytic capacitor tantalum, electrolytic capacitor polymer aluminum, super ultra capacitor, which is electrochemical. Then, electrolytic capacitor, this is non-polarized. These capacitors actually are polarized. Meaning to say, they have polarities, like this one. Negative side and the positive side. Okay? The capacitance is given as 2,200 microfarad with a working voltage of 50 volts. Okay. They can't be inverted in the circuit. It should be in correct polarity. Otherwise, they will be broken down. No? We will find out that one later on. Okay? The rest of the capacitors are non-polarized. All of these are non-polarized. Non-polarized. No? They can be connected in the circuit in any direction because they are non-polarized, and we have here the symbols for the capacitor. But for the electrolytic polarized, we have positive and negative side. No? Actually, before we proceed to the numerical code, there are two kinds of capacitors also, like resistors. We have fixed resistors and we have variable capacitors. We have fixed capacitors rather and the variable capacitors, no? The fixed capacitors and the variable capacitors. Okay, let us prove. We have here using this digital multimeter. Okay. Digital multimeters is also capable of measuring capacitance. Just set to this portion here, no? The range selector switch is positioned to this portion, no? Then select. We have here to select the unit. That is volt, that is ohms, that is farad, nanofarad. Because capacitance is also an electrical amount of capacitor in farad, microfarad, nanofarad, and picofarad. Okay, let us measure the capacitance of this capacitor. Okay, we have here for the metallized ceramic disc. Okay? It is 19.19 nanofarad. Okay? 0.19 nanofarad. Let us verify using this alligator clip. Let us clip using this alligator clip. Okay. So, the capacitance now is 9.68 nanofarad. 9.69 nanofarad. Okay, that is now the capacitance of this capacitor, no? 9.69. Okay. 9.69 nanofarad. 9.69 nanofarad. Okay. When you convert that one into micro, remember, nano is a prefix unit, no? We can have also microfarad. We can have also picofarad. Nano is 10 to the power of negative 9 farad, no? Nano prefix unit is equivalent to a scientific value of 10 raised to the power of negative 9. Whereas micro is 10 to the power of negative 6 farad. And pico is 10 raised to the power of negative 12 farad. Okay. When converting nano to micro, so it goes like this. Nanofarad to microfarad. You are converting a smaller unit to a larger unit. Remember? Nano is handling negative 9. Micro is handling negative 6. So therefore, nano is smaller than micro. So, the decimal point should be where? Just like kilo ohms to mega ohms. Kilo is a smaller unit compared to mega, million. Because kilo is 10 raised to the power of 3. Whereas mega, which is million, is 10 raised to the power of 6. So you are converting smaller to larger. If we have 1,000 kilo ohms to mega ohms, so what is the difference between these two? The difference is 3. Remember? 6 and 3, the difference between them is 3. So, just move decimal point. The decimal point of this 1,000 is after 0. Move 3 places to the left to make it 1 mega. So, 1,000 kilo ohms is equivalent to 1 mega ohm. But it is appropriate to convert this one into mega ohm in the sense that the electronic circuits always look and use the least number of digits. That's why you cannot you cannot encounter this value in a circuit or any electronic schematic diagram, because the electronic circuits or the electronic schematic diagram will always use the appropriate unit. So which of these two is appropriate? 1,000 kilo ohms or 1 mega ohm? So 1 mega ohm is actually the most appropriate. Just like this one. So we have here 9.69. So you move decimal point to the left. Decimal point is over here. The difference between these two is nano is negative 9, micro is negative 6. No? That is the way how we convert units. So therefore, 9.69 nanofarad, when it is converted into micro, it goes like this. 3 places to the left. That becomes 0.00969 microfarad. But among these two units now, micro and nano, nano is the most appropriate because it has only 1, 2, 3 digits, including decimal point, that becomes 4. Compared to micro, 0.00969, so there are more number of digits. So it can accommodate bigger space. So 1, 2, 3, 4, 5, 6, 7. So the most appropriate unit now is nanofarad. But when you are converting larger unit into a smaller unit, you have to move decimal point to the right. No? For example, we have here 0.035 mega ohms to kilo ohms. Mega is larger in unit because it handles positive 6, whereas kilo handles positive 3. So the difference between these two is 3. No? The difference, 3 and 6, the difference between them, or the gap between them is 3. So, when you are converting larger unit into smaller unit, you have to move decimal point to the right. How many places? 3. Because the difference between them is 3. 1, 2, 3. No? That becomes 35 kilo ohms. So, 35 kilo ohms and 0.035 mega ohms are the same. But we are always looking for the most appropriate unit. And the most appropriate unit now is 35 kilo ohms. Remember, that is the shorthand version for units conversion. No? Let us not intricate the situation. Let us always look for the easy situation. And this is now the shorthand version for conversion of units. No? Just remember, when you are converting larger into smaller, you have to move decimal point to the right. And when you are converting smaller to larger, you have to move decimal point to the left. How many places? That depends upon the power of every prefix unit. Kilo, mega, nano, micro, pico are prefix units. Ohms, ampere, hertz, volts are basic units. Okay? Okay, let us now come to the, okay, we have here. So, 9.69 nanofarad is actually the capacitance of this capacitor. We call it coded value because there is a numerical code here. No? What is the, this is the measured value, by the way, huh? 9.69 nanofarad is a measured value using a capacitance meter. Okay? So, what is now the capacitor code? We have here 103K. Okay, we have here 103K. 103K. And the voltage here 1 kilovolt. 1 kilovolt, by the way, is a working voltage or a dielectric strength. The strength of the insulator or the strength of the dielectric between the two conductor plates to withstand the applied voltage without breaking down. Okay? So I have here 3 here is indicates the number of zeros or a multiplier, which is times 1000. Or just write it automatically. 10 plus 3 zeros. Then, more or less, K is 10%, as what we have here. No? There is a tolerance. Okay? Voltage. Tolerance. K is more or less 10%. This is now the tolerances for the capacitor code. No? We are not using the color codes. Instead, numerical code printed on the surface of the body of the capacitor. It is marked there K. That indicates the tolerance, no? More or less. Okay? So, this would mean it is 10,000 and the unit is pico. Always pico, huh? Okay. Picofarad. More or less 10%. Then, we need to convert it into micro. So, micro is 1, 2, 3, 4, 5, 6. So, that becomes 1, 2, 3, 4, 5, 6, 0.01 microfarad. That is the equivalent value in microfarad. That is 0.01 microfarad for the 10,000 picofarad. Because you are converting a smaller unit, pico is smaller than micro. Remember that. Because pico is negative 12, whereas micro is negative 6. You are converting smaller into larger because the bigger the negative value, that is the smaller the value, no? For negative 12 is smaller than negative 6, okay? Negative 6 for micro. Okay. If it is nano, pico to nano, pico is negative 12, nano is negative 9. So therefore, nano is bigger in value. So when we convert pico to nano, the difference between them is pila. How much? Negative 12 and negative 9. It is 3. Unlike a while ago, pico and micro is 6 because pico is negative 12, whereas micro is negative 6. The difference between them or the gap between them is 6. That's why we move decimal point 6 places to the left. No? 1, 2, 3, 4, 5, 6. That's why it becomes 0.01 microfarad. 6 places to the left. We are converting smaller to larger. Pico to nano. So, 3 places only. 1, 2, 3. That becomes 10 nanofarad. So, among these 3 units, 0.01 microfarad or 10,000 picofarad or 10 nanofarad. Which is which? Which is the best or the most appropriate to use? So, of course, 10 nanofarad is the most appropriate because it has the least number of digits. Whereas here, 1, 2, 3, 4. So, it can accommodate bigger space. Much more for this picofarad. Much bigger. 1, 2, 3, 4, 5 plus a decimal point 6. So, much bigger. So, the most appropriate unit now is 10 nanofarad. So that is now the, go ahead here. The measured value actually is, how much is the measured value? That was 9.69 nanofarad. 9.69 nanofarad. Okay, let us measure it again. This one, di ba? Okay, we have it here. So select using this button, ohms, nanofarad. Okay, 9.68 nanofarad. That is now the reading of this capacitance meter. Measured value is 9.69. 9.69. So 9.69 nanofarad, the measured value. Okay, let us compute using the coded value. Because the coded value here is 103. 103 is 0.01 microfarad or 10 nanofarad. Okay, 10 nanofarad from 10,000 picofarad. Because when we convert 103, the result is 10,000 picofarad. We need to convert it into micro or nano because we are looking for the less number of digits. Okay, let us compute. We have here the coded value, di ba? 10 nano times 0.1 because K is 10%. K is 10% because the numerical code is 103K. Then we have here 1 kilovolt. Is that 1 kilovolt? Okay, 1 kilovolt. Converting 10% to decimal number, it results to 0.1 because 10%, decimal point is over here, 1, 2. That becomes 0.1. So therefore, this is, okay, 1 nanofarad is the product. To get the more, 10 nanofarad plus 1 is 11. 11 nanofarad. Whereas, to get the less, 10 nanofarad minus 1 is 9 nanofarad. So therefore, from 10 nanofarad as the coded value, the less is 9 nanofarad and the more is 11 nanofarad. And we have here the measured value. 9.69 is somewhere here. So therefore, this measured value is still tolerable. That capacitor is still good because it is still within the tolerance limit. Tolerance is the permissible deviation of the value from the specified value. Okay, we have heard the specified value, 10 nanofarad, based from the coded value, no, or numerical code. And when you compute the tolerance more, the maximum allowable deviation or the permissible deviation is 11. Beyond that one is no longer permissible. It is considered bad. Or below 9 nanofarad, let us say 8.9 is considered bad because they are not within the tolerance limit. No, just like in resistor also. Okay, that's the way we convert or read or translate the numerical code for capacitor into capacitance. No? And what is this 1 kilovolt? 1 kilovolt, by the way, is the working voltage or the dielectric strength, the strength of the insulator being used. What is this insulator? It is a ceramic. Ceramic is made of clay. No, yung lupa. So it is used as an insulator or dielectric strength that separates the two conducting plates. It has the ability to accept electric charge or voltage. No? Okay. So, whatever the working voltage, the applied voltage should not exceed that working voltage. Like for example, in this capacitor, okay, this capacitor, the capacitance of this capacitor is 220 microfarad and the working voltage is 16 volts. So meaning to say, the dielectric strength or the strength of the insulator, which is electrolyte, is capable of handling the applied voltage, the voltage that is fed to them, should not exceed to 16 volts. Okay, let us prove. So we have here okay, okay, let us prove if the 16 volts of this capacitor as a working voltage can withstand the applied voltage. Okay, we have here an AC-DC power supply. Okay, the output voltage here actually is DC, no? DC. Let us try to measure. So, the voltage over here, using this digital meter, set it to voltmeter. It is DC, voltmeter. But the voltage that we are going to measure is AC. So, therefore, set it to AC. We have here AC. Now, this AC voltmeter is appropriate now to measure the AC voltage, which is outputted by this transformer. It is the voltage here 25 volts. Now let us prove if really that voltage can be controlled by the dielectric strength 16 volts. Okay, let us measure again. Okay, we have here, so this is now the 16 volts. Okay, focus. We have here the negative side. And we have here, let us first disconnect, and the positive side of the capacitor. Okay. The negative and the positive. Okay, what will happen? If the applied voltage by this power supply is somewhere at 30 volts, including the peak value, and the amount of the working voltage of this capacitor is only 16 volts. Okay. Focus. We have here. The capacitor is over here. Okay. See?